All right, guys, let's hop right into this. First assignment. It's supposed to melt your brain. All right. So let's melt your brain together. All right. Yeah, catch the pun. Let's go. So before I begin, this assignment has a possibility. The explanation. The explanation I have could be wrong, right? So just follow it with your discernment. But I did my best, and I've coded it, and I worked it out, and I think it gives the best solution that everyone can follow. So, um, although I do have to say this just in case, so I don't have people upset. But anyways, let's keep going. So basically, this is the overview of the entire assignment. Um, I made it interactive, so if you click on one of these, it will shoot you to where it talks about each of these things. So if you click on arrival times, it'll take you to explaining arrival time, core request, core. That's kind of hard to see. SSD, etc., etc. SSD request, you can't really see that one, but there's a link there. And then everything else kind of repeats. Termination's not that hard and this stuff, but we do not talk about input and display in this video, and we do not talk about reads in this video. Just because those are not part of the output I'm going to be explaining. So one thing I want to go over is part of this diagram is key is this part. Is red lines mean no, green lines mean yes. So if I were to approach this path and I ask, is the ready queue empty? And you say no, I'm going to first, the green path is always taken. If red is present, red will complete before game. So that's all it's saying is if the ready queue is not empty, I will do this, and then I will do this. Same thing here, SQ empty, no, I will do this, and then I'll do a core request. That's all that means. Okay, what is the point of the assignment? Not that, definitely that. So this is a simple picture, okay? This is a great picture actually, but it leads a lot of like questions. What exactly is this thing? But let's break it down. So you have the CPU, you have the SSD, you have the ready queue, the SSD queue, input, and where's the schedule? Because you need a scheduler to determine, who should be in your core and who should be in your SSD. But it's not inside this diagram. Actually, you have to think about making it in your program. So your program is going to use a priority queue where you're going to organize. Basically, if you're using C++, you're going to use a constructor that says you're going to organize your structure of your priority queue to do it based on the times of each time coming in. You can look that up on how to do it. It's not that hard. But if you do need help, I can explain that later. But it's something you can Google. So basically, your main scheduler will work on the basis of time. Okay, and so the ones with the least amount of time are going to be served first. So they're going to have the highest priority, right? These are the suggested data structures. I honestly think these are the best data structures. I know you can use different ones and be as creative as you want, but we all want to go to bed, so use these data structures. You can have a normal queue of processes. So you can have a SQ, which is this one, and then ready queue, which is 2, A1. You're gonna have Boolean values, whether you're using this CPU or whether you're using this SSD. And then you're gonna have a priority queue of processes, which is your main queue, right? And then the process should have these 6 components. So you're gonna need a structure to store all of it. That's all for that. You're gonna need all of these to be global, right? Because every single one of your functions is going to be using your normal queue. It's going to have to check whether your CPU is empty and whether your main queue has something in it or not. So all of these have to be initialized before your functions. And these we'll talk about later, but you have to have them go global too. You're going to need a map, a clock time, obviously, and all that stuff. Okay, focus on the thing that will drive the program forward. It's a simple while loop, okay? All you're going to do is if your priority queue still has things to do, you're going to keep you know, keep it running. And basically, you're going to read the top value and save it. So in this case, you're going to read this top value, right? And what's the top value? It's this. I just put it linearly, horizontally, okay? Sorry, my microphone's acting up. And then you're going to pop the top from the main queue. So after you pop that, your main queue is only going to have this, right? Because you got rid of this one, and now you're left with just this. Set the clock time to that time that it has. Figure out what to do based on the command. So you're either going to have an arrival time or a completion event. So it's either going to be a start or some other command. So what do we put into our main queue and when? You're going to put processes with either completion times or arrival times. I can't emphasize that even more. I'm going to emphasize it later. But make sure you only have completion times and arrival times. This will make sense later. But please understand this. Where do the completion times come from? After the while loop starts. So you're going to want the completion times are going to happen after you pop these from the main queue with their start times. But you're like, hey, when do you add in the start times? Well, duh, from before the while loop starts, right? You're going to want to have start times. I call them arrival, but it's the same thing. Start times come before the while loop starts. So arrival times are associated with only one operation, completion times. So before your while loop starts, it only should have starts in it. Haha, no pun intended. How to read input to create this main queue before. You just, create an input structure, then create a vector of inputs. And here I put it in the main, but technically since we're making this input table, no, we're not. Yeah, you're going to want to read it in the main. And then make sure y'all are running this on WSL because that uses redirection. But hey, if you don't have it, Replit works too. At this point, we should know how many processes we have in the example above. So here we have 2 processes because we have 2 starts, right? And so here, now we're going to create a process table. So you can, this is a simple Python concept, or, you're going to use a list within a list or a vector within a vector, linked list within a linked list, which is bizarre, but you can do whatever you want. But all you got to do is create each list to have a list that can hold all of these elements, or not even you could honestly be smart and create a list of structures. So each element in the list is going to have a structure where it has all these elements. So you could, do something cool like that. It's just, how do you make this table work? So you use the input table to fill in the process table. So I have this input table, and then the indexes, you notice, we start from 0. And then look, the start line of this one is going to be here. The start line of this process is going to be 5. And these are just the way I defined it. You can define it any other way. I just thought, hey, -1 means it didn't start, and 0 means it has not started. You can do another method. It doesn't matter. There's no right way to do this or wrong way. Okay, we can create the main queue after creating these tables, right? Because now you just say for every PID, you could honestly use a constructor and just add processes. So since your main queue is of a type process, you're just going to add these as processes into your main queue. That makes sense? Like, you're going to have a main queue of structure processes. You're just going to add these in. Okay. Notice they are initialized with nothing for writes, reads, and whatnot. And notice before the while loop starts, we only have start times, right? Okay. Now we start the while loop up. Okay. While the main queue is not empty, it's the same process every time. While the main queue is not empty, we save the top. So that's going to be the top. Pop the top. After the top, we're only left with this one. Honestly, that should be a 0. But whatever. Accidentally left it at a 1 because it is now the only thing in the main queue. And we save the top to the clock time. So the time here is 0, so we set it to 0. Figure out the command. It's a start. So now we're going to understand the functions of the main. Okay, so here we just did that, right? If the command is a start, it must be an arrival function. Else, it has to be a completion function. That's all you need to know. So this is a simple if statement. And why I say function is because you don't want, I mean, you could do this all in one script, but just think how messy it's going to get. You want to use functions because you're going to want to send things to different places and want those functions to be reused again because you're going to be doing the same thing over and over again. So just use functions. This would be smarter to say as an arrival function and a completion function. So you handle the event in that arrival function, you handle the event in the completion function. That makes sense. In this arrival function, we're going to pass these as parameters minimally. So we at least need to know what process we're dealing with, the process table, the input table. And remember, we wanted to make our lives easier, so we made all the other variables global, right? So arrival continued. So a new process will always go to the core. That makes sense, right? Because you're coming in, you have to come in through here, right? You're either going to wait in the ready queue or going to go to the core, right? So therefore, the arrival will always be a core request function. See? Okay, that's the main queue, a new process, bop, goes inside. Okay, so this is the outline of an arrival function. Before we need the arrival function to do something, right? We created the function because we needed to do something. So we get the process, the current line. No, we change it, sorry. So we increment this by 1. So this was, remember the current line was -1, now it's 2. And how's it 2? It's 1 plus 1, which is 2. Here, the start line plus 1. Get the command from the input table. Now we take the command, and it's telling us it's a core 200. We send these updated parameters to the core request. So what have we updated? We updated the process table, right? We did not modify the input table. All we did is we read the command from it, right? You never change the input table. You only modify the process table. That makes sense, right? So your input table is never going to change, but where your processes are going to change, right? This is what you're using as a guideline to kind of change this, right? Because if you know the process number, you can find the current line and you can figure out what command it is on or where it is in the input table. So this is important to update so you can find the right instruction to use in your input table. This is also will be helpful in your debugging and whatnot. So we've done our arrival function. This is all it did. It incremented the current line and it got the command, right? This will always be core, like I said, because you're always going to the core, so it's going to be a core request function. You're not going to have an SSD, like how's it going to, no, that's not going to happen, okay? Just the diagram he made is pretty good, but yeah, you have to like kind of understand it. So here, incoming parameters, process table, input. Remember, those are like the minimum ones at least. So this function will do 2 things. Like this is an overview. The core is empty. We're going to just go to the core, right? If the core is full, we're going to have to wait right here in the ready queue. That's why it's B and then A, respectively. So in this case, we're not going to do this one this time because we just started our program. How can there be anything in the ready queue? We have to jump to the core, right? This function does, all these functions are void. We're not returning anything. All we're doing is we're just changing values here and there, adding things to vectors, adding things to queues, removing things from queues. Like there's nothing really being returned. I mean, you could make your program like that, but I think voids are smarter because you're just modifying things. And I hope that makes sense. So here's the action with our example. Obviously, we're going to do the first one because there's nothing in there. We find the completion time. Now, where did we get the clock time at 0? Remember, it's all the way back here that we popped the top and the clock time was 0. It's just I had to explain all this before we got here. But anyways, that's where that came from. It needs 200 because its first request is 200 there. And we push this back into the main queue using its completion time. Okay? So remember, the main queue, there's only completion times and arrival times, right? Because this is the time that it finishes is the clock time plus its time needed. Time needed is in our input table. Clock time is, what was popped from the top, the process, the time the process came in, which is 0 earlier, and so that's its completion time. Okay, so look, completion times and arrival times. That's key. That's the only thing you can have in your main queue, and it makes sense as you look at it more. So let's create a flowchart where we are now. So we have a main queue. We looked at it. We had an arrival time. We go to a core request because that's the only thing we can do, right? And the ready queue, there was nothing in the main queue that was using the core, so we could just go into the main queue and use the core, right? So just remember to set your CPU to full because we're using the core. This is our main queue now. We have at time 200, it's using the core. Now here comes process 1. It's like it starts at time 100, right? That's its arrival time. We start the while loop up again. We pop. Can't talk today. We save the top and we pop it. You see, saved it. Save the top one, and then we pop it, and this is the main queue. After we pop it, we get the clock time from this time right here, and we figure out the can't. It's an arrival event. We do the same thing. We change the process, current line, and guess what? It's a core. Who would have thought? Current line goes up. But this time, we have a problem because our core is being used, right? It's being used by process 0, right? So our only thing to do is we can only wait in this ready queue because right now, according to what we popped into our main queue, process 0 is going to finish at time 200. So the only thing we can do is go into this ready queue. So that's why I have this big square here. Honestly, this guy gets too much love in this slide, getting all the space, but you see what I mean here. So if the core is full, remember we set it to full, we change the status to ready to here. 1 is 2 is ready, and this is just my conventions. You can make it whatever you want. And we push this process into the ready queue with its time needed. Okay, so it needs 80 in the core, and look, it needs 80 in the core here. That's it, and it's on current line 6, right? So let's create a flowchart of where we are now. We came in arrival time core request. The core was being used, so we couldn't push it into the main queue. We had to push it in the ready queue. This is how it looks, right? All good in the hood. All right, start the while loop up again. We're only focusing on the main queue here. We pop the top. Main queue is empty, but not for long. We'll see that in a second. Save the top time. It's 200. Hey, guess what? It's no longer arrival times. We're now dealing with completion events. So there's 2 main types of completion events with different sub-events, right? Either I leave the core or I leave the SSD, right? Right? Why isn't there a completion event for the user? Because there's no buffer for the user, right? So the user, it doesn't have a buffer. So whatever it's being used is just going to be thrown back. It's going to get its time in the main queue. It's going to get its completion time. The reason we need one for these is because when this one ends, we have to always check whether there was one waiting. That's why they get their own function. But anyways, we'll explain that more later, but whatever. So there are main 2 types with different sub-events. We got one, they either terminate, they leave, like go to the SSD, or they go to the input display, right? The completion events can do that, right? SSD completion, upon completion, they can only go to the core, right? They can't just fall out of the computer. Anyways, this was a slide that had a little visual that worked with the PowerPoint, but I don't have the PowerPoint running, so whatever. This thing was supposed to move this way, and this was supposed to go. So the general principle for both is if something was waiting for the core of the SSD, I'm going to first have to check whether there, if there was, right? So if I've left the room and I've completed my task, right? If something was waiting, I have to schedule it in the main queue, right? That's all we're doing. If there was someone in the room, I let them have the room, but the room is still full. If there is none, that means I left this room. The room's now empty. This B is supposed to move. This B is supposed to move. And this A is supposed to come in. These are different cases, right? So now this is actually like the main idea. So set the core to empty. If the process, schedule the process if waiting in the ready queue. If there's a process waiting in the ready queue, we do this first. We schedule it. to let it use the core, and then we figure out what this guy's supposed to do next, right? So either it terminates, it goes to SSD, goes to input display, yada yada. Same thing with SSD. Now let's create a flow chart of where we are now. Now it's getting a little bit too big, so let me zoom out. Wow. So we main queue, we had a completion time, we had a core, right? Now we're technically here, but whatever. Again, I'm saying if red is present, red will complete before green. Okay. Refresh where we are again, right? We have process 0 coming out. We have process 1 in the ready queue. So pop the top, clock time, core. Give me a second. So basically, right here, it's the same slide as before. We're just a refresher. So we pop the top. It comes in at time 200, right? The main queue is now empty, and the clock time's 200, and we know it's a core completion event. Core completion event outline, more like code, pseudocode. We set core to empty. Ready queue if ready queue is not empty, top is equal, pop it. Then we send the top to the core request, right? With all its other things, right? Which would be, the input table, process table, whatever you think is important. Then if the current line is equal to the end line, we terminate. Else, increment the current line by 1. If read or write, we do SSD request, input, push it back into the main queue with completion time, right? With our example, we're going to do the first one, right? Because there is something in our ready queue. So we're going to schedule that process waiting in the ready queue. Then do this stuff, right? So this guy comes out right here. Remember, our clock time's 200. You can go back and look if you want. We look at its time it needs. It's 80. And its completion time is going to be 280. So we push this back into its main queue using its completion time. Our main queue now looks like this. Again, completion times and arrival times only. If we look at our table, it's now running, right? We put it in the running state. We'll change this one in a bit. This function's not finished yet, right? We've just handled the aftermath of it leaving, like process 0 leaving and process 1 coming in. Now we have to figure out what process 0 needs to do. So now we figure out, hey, it needs to go to the SSD, right? Because we incremented the current line by 1. So we know the current line is now 3. And we look at its next process. Or its next event. So it's a write. So we go to the SSD, right? Haha, right. Here's the example. Here's the one that we're going to send to the SSD. We did that already. SSD request is just another recap of it. A flow chart where we are now, right? We came here, core, ready queue was not empty, so we went to the core request and we pushed that into the main queue. We're done with that red line. Now, what do we have next? We have our SSD request. Okay, SSD request overview. SSD request can be 2 commands, reads or writes, right? Reads have 2 things to it. It can be physical or logical. To understand this better, read Dr. Paris' slides on that. But basically, physical costs us 0.1. Writes are always physical. And this is like a more colorful example. So basically, we have a request. If it's a read, it could be logical or physical, right? If it's logical, we go straight to a core request. It doesn't cost us anything. We don't even have to touch the SSD. So basically, if we have a logical read, we just go, we pass all this. And it's like, you pass go, click 200. And you just go back here. You get another core. It's obviously going to be a core request. Like, where else can it go, right? Or it can be a write. And if it's a write, physical write, writes are only physical. That's why I just said phys write. We either push it into the SSD queue right here, or we push it into the main queue where it's using the SSD. That's it. And I did all the color coding so you can look at that. I don't want to spend too much time on that. Quick note. Oh, so remember when we said B size -1? This will make sense when you go back to Dr. Paris' slides and you look at buffer reads. Because if the buffer has been read, we'll know if it's greater than 0. But if we set it to -1, we know that it's not. So we'll see what the buffer is, and then we'll, do the other stuff. but I won't spend too much time on that because I think he explained it well on his slides. So again, we're revisiting the core completion we had, and we had an SSD request. Remember? So it was this process right here, process 0. At time 200 it came in, and SSD requests only take us 0.1 seconds if it's physical, right? And it has to be physical because it's a write. Writes always are physical, so they're always going to cost us time. So this write costs us time. We update physical writes by 1, right? Because when it goes back into the main queue, it's gotten its time. So, you know, it's done its physical write. And if you're confused where we got the clock time, just go back. Flow chart where we are. This is kind of like the general one. This is pretty much the whole program right here. If you follow this flow chart, you will ace the assignment, okay? I took time making the flow chart, so just follow it, please. Okay, start the while loop up again. Here we go. Guess what? Process 0, it's gonna finish faster. So, because process 1 is still running till time 280, so this one comes out first. We save the top, main queue after the top, after we pop that one, and the clock time's 201. Figure out what command we have. So we have a write, so it has to be a completion event, right? And what type of completion event? An SSD completion event. So remember, if we finish with the SSD, we look at whether anything was in the SSD queue, and those processes get an SSD request, and then we'll do a core request. If this is a no, then we just do a core request, right? Because if you remember that diagram up here, like if we finish here, if there's something waiting, we put it back in here. If not, we let this guy go here, okay? That's all this thing is meaning right here. Anyways, same thing I just said. We set our SSD to empty, right? Because this is a completion event. So we're done with the SSD, so we set it to empty. If any process was waiting, we send it to the SSD request. There's nothing waiting for the SSD. Freaking loser. Anyways, we look at the next command, we increment the current line. So after it's done using the SSD, it's saying now I want to use the core. So we've already made a core request function, right? So we just send the process there. You see how these functions are nice? And we're at the end of this, we're at the last thing the guy needs. But too bad, so sad, it's being used. Why? If you remember, a pure process 1 is using the core. So guess what's gonna happen? At this time, remember, process 1 is running it in the core. This guy's gonna have to wait in the ready queue with the amount of time it needs. It's 30 seconds, but it's still done its one right, so it's done its time. Remember, I need 30 seconds. Time needed right here is 30 seconds. 30 milliseconds or whatever time they use. Pushes process into the ready queue with its time needed, and we're done with that. Start up the while loop again. Process 1 comes out at time 280. Main queue empty. Clock time 280. Completion event again, right? Core. Done with the core. Same thing as before. We check whether there was something waiting for the core. Was there? Yeah, it was this guy we just put in. So we let that guy come out right here. Right? If the core is empty, it's going to be empty because, it's core completion, but whatever. You do all these things. It's not empty. Do a core request, and we push this into the main queue. From the main queue, 280. This 280 came from the clock time up here, remember? Process. So we've done the aftermath of, finishing the core. We scheduled the next thing that was waiting for the core, which was P0. So this thing's now using the core in the main queue. We've updated our main queue. So now we have to determine what that process that just left the core next step is. So here, its next thing it wanted was a write, right? We go to the SSD, right? The only thing it can do, SSD. I mean, it can do these other two, but that's not what it's asking for. Process at command 1, write. Okay. Is write? Is the SSD full? No. So we push it into the main queue, right? with its completion time. 280 plus 0.1. And we update the physical rights by 1. And remember, we pushed this in earlier. This was the one waiting in the ready queue. And then this is the one we have right now. Just go through the slides here. This is what came in. You notice it was 0. But because it was an SSD request and it got the SSD, it went up by 1. So I hope that all makes sense. We're at line 7. Start the while loop up again. We have the completion event for the write. Right? Yep. We know the write has finished, so we update the process table. We're now done with this line. It's a completion. So now it needs core 40 for this top one. But again, the core is being used by process 1 till time 3:10. So it goes back waiting into the ready queue. P1 waits in the ready queue with its time needed, 40. Pop the top, main queue empty, time 3:10. Core completion event, right? Schedule the one waiting with process 1, right? Give it its completion time. The clock time, 3:10, which is the time of the one we just popped, right? And here we go. Add that back into our main queue. So if this one finishes at 3:50, right? Pay attention to how I'm updating the table. Make sure you follow this. Don't update the current line. Just the status. Because the current line only updates in the completion functions, not the request, okay? Because the request just changed the status. The current line updates after it's completed, right? And then we've done the aftermath of it leaving. So now we have to do ready queue empty. Look. The end line is equal to the current line for process 0. So now it's at a termination. So this is where we print our output. 3:10, 1 physical write. 1 running is process 1 is running. This means process 0 is terminated. So we start that main loop up again. We only have 1 left. It comes out, 3:50, main queue, clock time 3:50, core. We terminate. There's nothing in our ready queue. That one's already terminated. So this is the last one to terminate. Because the current line is equal to end line, states -1. Bah, termination. This one should say 0 terminated. No, this should say 1 terminated. But I accidentally left it at 0. Whatever. And that's all you need to know. And that's the end of the assignment. So if you go to any of these, even at the beginning, there was the same slide with the same links. And you're like, hey, I'm confused. What do we do? We need an arrival time. There. Bang. Right there. Okay? And that works for the main functions. So this is a function. Arrival times is a function. Completion times is a function. SSD completion is a function. Core completion is a function. Core request is a function. SSD request is a function. That's why they each have links. Okay? These are mostly just if statements. If is right, do this. If read, then if logical, read. This you'll have to determine whether it's a logical read based on the buffer size. But these are your functions. The ones that have these links are all your functions. All the rest are mostly if statements or calculations, okay? And that's it. And this is important too. That's the general principle behind the assignment. The and.